These are the answers to the thermochemistry practice quiz. Number 1. Write the equation that is used to calculate the kinetic energy of a moving object, and that equation from physics is kinetic energy is equal to 1/2 mv squared, or 1/2 mass times velocity squared. Now in number 2, we have to calculate the kinetic energy of a shot put that has a mass of 16 pounds and an initial speed of 12 miles per hour. Let's convert pounds into kilograms using the conversion factor. So we're going to divide by 2.205, going from pounds to kilograms. We get 7.256 kilograms. I'm not going to round that off just yet because I'm not done. Let's convert 12 miles per hour into meters per second. So miles to meters involves multiplying by 1,609. And then hours to seconds, we have to put hours on the top and seconds on the bottom. We'll divide by 3,600, so 60 times 60. If we do this math, we get 5.363 meters per second. Again, I'm not rounding off because I'm not at my final answer yet. Kinetic energy is equal to 1/2 mv squared. So if we do this math, we get 104.3 joules. Since our measurements have only two significant figures, let's round off 104.3 to two significant figures. We have to do this by putting it in scientific notation, so we get 1.0 times 10 to the second power. And again, as you can tell, the units are in joules. All right, number 3. For each of the following questions, examine each diagram that contains a before and an after situation. The system is defined as everything inside the rectangle or the cylinder. We have to pick one of the following. Work being done by the system is losing heat. Work is being done on the system is gaining heat. In this example, work is not being done because the size of the container is constant, so a gas is not being compressed, and gas is not expanding, but the size of the arrows indicate that the particles are moving faster in the after picture. So if the molecules are moving faster, then they are getting hotter, they're gaining heat, so the system is gaining heat and Q is positive. In part B, we have particles that are moving with a slow speed, so small arrows, and now it appears like they're not moving at all. Perhaps they're just vibrating in place. So most likely this is a liquid turning into a solid, and at this point, if the liquid turns into a solid, it must be losing heat, so it's getting colder, and so Q is negative. In part C, work is being done to compress the gas. So work is being done on the system, so W is positive. And then finally, the piston is being pushed up as this particular sample of dry ice undergoes sublimation. So work is being done by the system, W is negative. In number 4, we have a reaction in which the delta H is negative. When delta H is negative, the reaction is exothermic. This is an exothermic combustion reaction. And so if we know it's exothermic, that means that the energy is going to decrease as we go from reactants to products. So we are looking for energy released. That means we're looking for a down arrow as we go from a higher level of enthalpy to a lower level of enthalpy. So the correct answer cannot be the first two boxes. Well, the problem with this last diagram is that we need to start with CH3OH and O2 as the reactants. Since the reactants are not carbon dioxide and water, that makes that picture or that diagram incorrect. So the correct answer is this third diagram that starts with CH3OH and oxygen, O2, and then it releases 1,453 kilojoules of energy as it moves toward the products, CO2 and H2O. In part C of this question, we are given experimental conditions in which 123 kilojoules of energy is released. And we have to convert this into grams of carbon dioxide gas. So based on the balanced chemical equation and 1453 kilojoules of heat released, our first conversion factor is going to put kilojoules on the bottom and moles of carbon dioxide on the top. So the 2 comes from the coefficient in the balanced chemical equation. For every 2 moles of carbon dioxide that are produced, 1453 kilojoules of energy is released. Now all we have to do to go from moles to grams is use the molar mass as determined by periodic table calculations. So 1 mole of carbon dioxide weighs 44.01 grams. And if we do this math, we get, rounding off to 3 significant figures, 7.45 grams of carbon dioxide. All right, well in number 4 we had an exothermic combustion reaction. This looks like an endothermic reaction because delta H is positive. How many kilojoules of heat energy are required in order for 575 grams of ethanol to be consumed? If we go from grams of ethanol, C2H5OH, to kilojoules, our first step is to go from grams to moles. So from the data on the periodic table, from the molar mass of ethanol, we can divide by 46.068. And now to go from moles to kilojoules, in the balanced chemical equation, 35 kilojoules of heat are absorbed for every 1 mole of ethanol. Now we can do this math and round off our answer to 3 significant figures, and we get 437 kilojoules of energy. All right, on to part C of number 5. This is a conceptual question. Do you predict that the value of delta H for the reaction shown below, which has liquid ethanol instead of gaseous ethanol, should this delta H be less than, greater than, or equal to 35 kilojoules? Since we are going from a gas to a liquid, there should be a difference in energy between the gas and the liquid state. The liquid phase is at a lower energy level than the gaseous state. This should make sense to us because evaporation, or liquid to gas, is an endothermic process. Therefore, if we absorb energy going from a liquid to a gas should be at a higher level, liquid should be at a lower level. Now, if our diagram looks like this, going from reactants to products, but then we switch from gaseous ethanol to liquid ethanol, which is at a lower energy level, the difference between the reactants and the products should be greater than 35. Now, this diagram hopefully makes sense to you, but I'm going to go ahead and say this in words. The enthalpy of liquid ethanol should be lower than the enthalpy of gaseous ethanol. This can be explained because liquid ethanol is more stable. Heat energy is released when going from a gas to a liquid. So the liquid has a lower energy level than the gaseous state, and as you can see in this diagram, the difference in enthalpy between liquid ethanol and the products, C2H4 gas and H2O liquid, that difference should be greater than 35 kilojoules. Might be nice to draw the picture to help you visualize this. All right, moving on to number 6. Part A, calculate the number of kilojoules of energy required to heat 3.5 moles of aluminum metal from 22 degrees Celsius to 93 degrees Celsius. There is an equation that we learned in this particular packet, in this unit. Heat equals mass times specific heat capacity times delta T, or the change in temperature. Notice that the specific heat capacity is in joules per gram degree Celsius. So we have to multiply that number times the mass and the change in temperature. Now the mass of aluminum can be determined by using the periodic table. To go from moles to grams, we'll multiply by the molar mass of aluminum, 26.98. And so right now our calculation involves 94.43 grams of aluminum. The specific heat capacity is 0.91 joules per gram degree Celsius, And the delta T for this particular experiment, the change in temperature, 93 minus 22, is 71 degrees Celsius. Now let's go ahead and calculate heat. So mass times specific heat capacity times delta T. We get our answer in joules. We get 6,101 joules. Divide that number by 1,000, 6.101 kilojoules. Our limiting measurement is the temperature, so we'll round off our answer to two significant figures, 6.1 kilojoules of heat. Okay, on to part B. In part A, we calculated the amount of heat. In part B, we're going to calculate the final temperature of the titanium sample after it was heated. So we know we have 21 moles of titanium. Let's convert that into grams using the periodic table. So titanium is 47.87 grams per mole. And this gives us a value of 1,005 grams of titanium. Let's move on to our next bit of information. We don't know the change in temperature, but we have the total amount of heat, we have the specific heat capacity of the titanium, and we have the mass. Let's go ahead and solve for delta T. So if Q equals mc delta T, the heat is 3.9 times 10 to the 4 joules. The mass is 1,005 grams. The specific heat capacity is 0.54. And our delta T, based on this math, works out to be 72 degrees Celsius. That is not our final answer. That is the change in temperature. So we have to add that to 25 degrees Celsius. Our final temperature is 25 plus 72, or 97 degrees Celsius. All right, let's take a look at part C. We have the mass of an unknown metal. We have the total amount of heat absorbed, and we have the delta T. What we don't know is the specific heat capacity. Let's go ahead and plug in what we know. 2.5 kilojoules. That's going to be 2,500 joules. The mass is 84 grams. And the delta T, the change in temperature, 99.6 minus 21.5, that's a difference of 78.1 degrees Celsius. When we rearrange the equation and solve for the specific heat capacity, we get 0.38 joules per gram degree Celsius. All right, this is part D, another conceptual question. We have to think about which sample of metal, the aluminum or titanium, is going to absorb more heat. So each sample was placed in boiling water, that's 100 degrees Celsius. Each sample has the same mass, and then the hot metal was placed in 200 grams of room temperature water at 20 degrees Celsius. So whichever metal absorbed more heat in the boiling water is going to cause the room temperature water to be at a higher final temperature. So is it the aluminum or the titanium that is going to raise the temperature of the room temperature water to a higher level? Well, sample A, which is going to be in this case the aluminum, will cause the water to reach a final temperature. Let's talk about why that is. Each sample has the same mass. Each sample was placed into boiling water. But since aluminum has a higher specific heat capacity than titanium, aluminum will absorb more heat when placed in boiling water. Therefore, the aluminum will transfer more heat to the room temperature water, causing it to reach a higher final temperature. Now that's all great in terms of conceptual understanding, but some of you watching this video might like to see the numbers, the math. So if we needed to actually calculate the final temperature of the water, we could do it. It's based on relatively simple algebra and the first law of thermodynamics, which has to do with the law of conservation of energy. What that means is that the heat that is lost by the metal is going to be the heat gained by the water. We have 200 grams of aluminum, and we know the specific heat capacity of that metal. initially it's in boiling water, so it's 100 degrees Celsius, and then it cools down to a final temperature. We just don't know what that is. The room temperature water happens to be 200 grams. Its specific heat capacity from earlier problems that we've seen in the packet is 4.18 joules per gram degree Celsius, and its initial temperature is 20 degrees Celsius, and its final temperature is, we don't know. But it's the exact same temperature as the hot metal that used to be in boiling water. In other words, they will reach thermal equilibrium. So the hot metal and the room temperature water will eventually reach the same final temperature X. And based on the law of conservation of energy, we can assume that the heat lost by the metal is equal to the heat gained by the water. Now it becomes a simple algebra problem. So the mc delta T for the metal is equal to the mc delta T for the water. We'll plug in all the information we know. The delta T is written as a positive value. So I wrote 100 minus X, and I wrote X minus 20. So X is going to be some temperature in between 20 and 100. And I wrote the delta T so that it would be a positive number. That made my math a little bit easier than trying to impose a minus sign on one side of the equation. Well, I can cross off the 200 grams because they are the same on both sides. I can distribute by multiplying, and I get 91 minus 0.91x on the left, and 4.18x minus 83.6 on the right. Let's go ahead and combine the like terms and solve for x. Now x is 34.3 degrees Celsius. That's the final temperature of the water when the hot piece of aluminum was added to it. That's supposed to be a higher value than if we had used titanium. Let's go ahead and prove that point. So I'm going to change from aluminum to titanium, and my specific heat capacity is 0.54. And when I do this math and solve for x, I get 29.2 degrees Celsius. So this might help some of you that wanted to see the numbers, that the aluminum will be raising the temperature of the water to a higher value because it absorbs more heat. Again, aluminum has a higher specific heat capacity than titanium, and therefore will cause the water to reach a higher final temperature. All right, this is number 7. We're given a structural formula for a chemical called phenanthrene. Write a balanced chemical equation for the complete combustion of 1 mole of phenanthrene. If we count the number of carbons and hydrogens in this molecule, we have 14 carbons and 10 hydrogens. So our formula for phenanthrene is C14H10. This is a combustion reaction, so plus oxygen, O2, and the products are carbon dioxide and water. We have 14 carbons, so I have 14 on the right. 10 hydrogens, I'll put a 5 in front of the H2O. And now there are a total of 28 plus 5, or 33 oxygens on the right. I'm going to use a fraction, so I can say 33 halves, or 16.5. I'm not going to go back and double each and every coefficient because they wanted the combustion equation for 1 mole of the phenanthrene. Okay, so we're done with that particular question. Let's move on to number 8. In number 8, we have an experiment involving a bomb calorimeter. 5.00 grams of phenanthrene is combusted. The temperature of the calorimeter increases from 23.5 degrees Celsius to 46.1 degrees Celsius, and the heat capacity of the calorimeter is 8.74 kilojoules per degree Celsius. So our first step in this problem is to calculate the number of moles of phenanthrene. Using the periodic table and the formula C14H10, I can convert 5.00 grams of C14H10 into moles. The molar mass is 178.22 grams. I get a small number. I'll round off my answer to 3 significant figures. I get 0.0281 moles of phenanthrene. Now on to part B. Calculate the delta T, that's just the difference in temperature. 46.1 minus 23.5. My delta T is 22.6 degrees Celsius. We're not going to do MC delta T in this case because there's no grams to cancel out. But we are going to multiply 8.74 kilojoules per degree Celsius times the delta T, and we get 197.524. Let's round that off to 3 significant figures, so 198 kilojoules. Now that we have 198 kilojoules, recall our answer to part A, 0.0281 moles. All we have to do in this problem is get the delta H, which is in kilojoules per mole. We're going to take the 198 kilojoules, divide by the number of moles of phenanthrene that was burned, and we get 7,046 kilojoules. Should this value of delta H for this reaction be positive or negative? Well, remember, it's an exothermic reaction. An exothermic reaction is going to release heat to the surroundings. This is why the temperature increased in the calorimeter. The thermometer is always part of the surroundings. Therefore, the answer is negative 7,046. I'm rounding off to 3 significant figures. So negative 7,050 is the answer to part D. And we know that the sign of delta H is negative for an exothermic process, so be careful about that. All right, let's move on to number 9. Now if we compare number 8 and number 9, in number 8 we had 5 grams of phenanthrene that was burned. In number 9 we have 10 grams of phenanthrene that was burned. So is the value of delta T going to be less than, greater than, or equal to the answer that we got in number 8? Well, if you're burning twice as much fuel, in this case 10 grams, more heat will be released. Therefore, the temperature change in the calorimeter should be twice as much. It should be greater. Well, if we have twice as much heat released in this experiment because we're burning twice as much fuel, let's see what happens about delta H. Do you predict that the absolute value of delta H will be less than, greater than, or equal to the answer we got in number 8? Well, if you said it was double, it's double the heat, but it's not going to be double the delta H because it is a ratio. The absolute value of delta H should still be the same as it was in question 8 because we're doubling both the number of moles of phenanthrene and the amount of heat released. The ratio of kilojoules to moles is the same, and therefore the value of delta H is the same. This is not the equivalent of multiplying all of the coefficients by 2. This is a question of using twice as much fuel in the next experiment. Twice as much heat, but we also have twice as much moles, so the ratio and delta H should be the same. Okay, let's take a look at number 10. This is a Hess's law problem. We are given 3 different thermochemical equations, and what we need to do in this problem is to combine these 3 equations in a special way so that when we add them together they will equal the target equation that is listed in the box. The first chemical I see in our target equation is C2H4. So where is C2H4 in the equations above? Well, it's going to be in this third equation, but it's on the wrong side. So if we flip or reverse this equation, I can get 1 mole of C2H4 on the left. As a result of reversing the equation, now the delta H becomes negative 52 kilojoules. Next chemical I'm going to look at is CF4. There should be 2 moles of CF4 on the right in our target equation, but CF4 is listed in the second equation on the left, so we have to flip that equation and also multiply by 2. When we do that, we now have a delta H which is not positive 680 but rather negative 1360. So we change the sign and multiply by 2. Finally, I need to get 4 moles of HF on the right. So I'm going to multiply this first equation by 2 so I can get 4 moles of HF. Now my delta H for that reaction after multiplying by 2 is not negative 537 but actually twice that, so negative 1074. Before we add these 3 equations together, let's go ahead and cross off the things that are not going to show up in the final equation because they appear on both sides. So carbon gets crossed off, hydrogen gets crossed off. Everything else is going to show up in the overall equation. That's 1 mole of C2H4, 6 moles of F2, 2 moles of CF4, and 4 moles of HF. Adding the delta H's together, we get negative 2,486. Again, this is a good example of Hess's law. All right, number 11 is also an example of Hess's law. Our target equation has 3 moles of nitrogen dioxide, NO2, 1 mole of H2O, and on the product side we have 2 moles of HNO3 and 1 mole of nitrogen monoxide, NO. So I will take this particular equation and reverse it so that the NO2 is on the left. I also have to multiply it by 3. So negative 58 now becomes positive 174 after it was reversed and multiplied by 3. In our next example here, if I take this equation and multiply by 1/2, I can get 2 moles of HNO3 on the right. So as a result of multiplying by 1/2, negative 256 for the delta H now becomes negative 128. And then finally, I'm going to reverse this equation so that I can get the nitrogen and the oxygen to cancel out. So if you're wondering about the nitrogen monoxide, don't worry. We're going to have 2 moles of NO on the left, but 3 moles of NO on the right. So the net difference will be 1 mole of nitrogen monoxide on the right. So it's all going to work out. Let's cross off the things we don't need, which is nitrogen goes away. I have a total of 2.5 moles of oxygen. So that gets canceled out. And 2 moles of NO on the left, 3 moles of NO on the right. That's a net difference of 1. Everything else works. 3 moles of NO2, 1 mole of H2O, 2 moles of HNO3, and 1 mole of NO. And the total delta H, when we add these 3 equations together, is negative 137 kilojoules. All right, number 12, we are writing balanced equations, and we are forming exactly 1 mole of a certain compound from elements in their standard states. So for Na3PO4, the elements are sodium, phosphorus, and oxygen. Remember that oxygen is diatomic, sodium and phosphorus are solids at room temperature, oxygen's a gas. We'll balance it by putting a 3 in front of the Na and a 2 in front of the O2. In our next example, we have nitrogen, hydrogen, and oxygen. They're all diatomic gases. Nitrogen's already balanced. We have 2 on both sides. I need 4 hydrogens and 3 oxygens, so I can use fractional coefficients if I need to. All right, so these are correctly balanced. Formation of 1 mole. Let's move on to number 13. Number 13, solid tetraphosphorus decaoxide, so P4O10, reacts with liquid water, H2O, to produce phosphoric acid. Now, since phosphate is PO4 minus 3, then we need 3 hydrogens to go with it. So H3PO4 is the formula, and it's a solution of aqueous phosphoric acid. This equation is not balanced. We have 4 phosphorus atoms on the left. Let's put a 4 in front of the phosphoric acid. Now we have 12 hydrogens on the right. Let's put a 6 in front of the water. I now have 16 oxygens on each side, so it is balanced. Remember that we do products minus reactants for enthalpy of formation. So we need products, in this case 4 moles of the phosphoric acid. So 4 times negative 1288, these are all in kilojoules. And then minus the reactants, that would be negative 2940 for the tetraphosphorus dicoxide, and then plus 6 times the number for water, negative 286. If we do this math, our delta H, which is our answer, is negative 496 kilojoules. All right, isopropanol has 3 carbons, 8 hydrogens, and 1 oxygen. So its formula is C3H8O, and it's a liquid. It undergoes combustion, which means we have to react it with oxygen gas, so plus O2, and it produces carbon dioxide and water. This equation is not balanced yet. We have 3 carbons. Let's balance the carbons. We have 8 hydrogens. We'll take care of that. And on the right, we have 6 plus 4. That's 10 oxygens. So to get 10 oxygens on the left, I've got to make a fraction, 9/2. I might leave it like this, except it does say using the lowest possible whole numbers. Let's go ahead and multiply each coefficient by 2. So our final coefficients are 2, 9, 6, and 8. All right, moving on to the heats of formation for this combustion reaction. We have products minus reactants. So 6 times the number for CO2 plus 8 times the number for water, and then minus the reactants, 2 times the number for isopropanol, and of course oxygen is 0 because it is an element. If we do this math, we get the delta H for this reaction, negative 4,016 kilojoules. All right, this is number 17. This has to do with breaking bonds and forming bonds. First, let's balance the equation. We need 2 nitrogens on the left, and now we have 6 chlorines on the left, so this is balanced. We're going to use the table in number 18 to keep track of the bonds broken and the bonds formed. Let me go ahead and talk about the structural formulas of these molecules. So NCl3 would look like this. We have 2 molecules of them, or 2 moles. Nitrogen is a triple bond. The Lewis structure looks like this. And then finally we have chlorine. That would be a single bond. We have 3 molecules, or 3 moles of chlorine. So the bonds that are being broken would be 6 NCl bonds. And the bonds that are forming would be 1 NN triple bond, and then 3 ClCl single bonds. So we're breaking 6 nitrogen-chlorine single bonds. We are forming a nitrogen-nitrogen triple bond, and we're forming 3 chlorine-chlorine single bonds. Let's go find the table of bond enthalpy data so we can keep track of these numbers. The delta H is going to equal the sum of the bonds broken, which is an endothermic process, minus the sum of the bonds formed. Again, that's an exothermic process. So I found nitrogen chlorine. It comes in at 200, so we have 6 times 200. And then I found nitrogen-nitrogen triple bond at 941. And then a chlorine-chlorine single bond is 242. So it's going to be bonds broken minus bonds formed. The minus is because forming a bond is an exothermic process, so we have to add a negative sign to the value. So 6 times 200 minus 941 plus 3 times 42. So I've done that math. 6 times 200 minus the sum of 941 and 3 times 242. So my delta H for this reaction is negative 467 kilojoules. Bonds broken minus bonds formed. All right, 19, we have to balance an equation. We have 2 carbons on the left. Let's put a 2 right here. We have 4 hydrogens on the left. Let's put a 2 right here. Now I have 6 oxygens on the right. so I can put a 3 there. So it's balanced. Use the table below to keep track of bonds broken and bonds formed. Let's go ahead and draw out what these molecules look like to make sure we have singles or double bonds, whatever it happens to be. C2H4 is going to contain single bonds and one double bond between the carbons. So I have only one of those molecules. Oxygen happens to be a double bond between the oxygens, and I have 3 of those molecules. For carbon dioxide, it's going to be 2 CO double bonds per molecule, and I have 2 carbon dioxide molecules. And then finally I have 2 water molecules. So the bonds I'm breaking include the following: 1 carbon-carbon double bond, 4 CH single bonds, and 3 oxygen-oxygen double bonds in molecular O2. What bonds am I forming? A total of 4 carbon-oxygen double bonds and a total of 4 oxygen-hydrogen single bonds. So I'm breaking a CC double bond, 4 CH single bonds, and 3 oxygen-oxygen double bonds. That's what I'm breaking. The bonds I'm forming include 4 carbon-oxygen double bonds and 4 OH single bonds. So you might have to draw these molecules out to convince yourself what kind of bonds you are breaking and forming. Let's go find these values for bond enthalpy in the table. Bonds broken minus bonds formed. So there's the CC double bond at 614. A CH single bond is 413. And an oxygen double bond as found in O2 is 495. That's endothermic. That's a positive value. Now for the exothermic, what I'm actually forming and then releasing energy, I'm going to look for the carbon-oxygen double bond. That would be 799. I've got 4 of those. And then the OH single bond, 463. So the math I'm doing is 614 plus 413 times 4 plus 495 times 3. That's all the stuff I'm breaking. And what I'm forming, that would be minus 4 times 799, and obviously minus 4 times 463. So I did this math, bonds broken, minus bonds formed. I kept track of everything, and I end up with a total of negative 1297 kilojoules for the delta H. Now, this represents the final question from the Thermochemistry practice quiz. I hope that all of these answers and explanations were helpful to you. Thanks for watching, and good luck studying for your quiz.